Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ngā mihi nui, he mihi mahana kia koutou. Thank you for coming along to our second virtual science talk. My name is Dr. Ben Payne and I work here at East Coast Lab. We're really sorry to keep you waiting. We've had a few technical issues with Facebook Live, but thanks for coming along. Last Thursday, we heard from Dr. Kate Clark and Dr. Laura Wallace, and their brilliant science is informing us about what's happening a short distance from our shores on the Hikurangi subduction zone. Tonight, two different but equally awesome scientists will be continuing the conversation. The talk is focused on their involvement with developing scenarios for what might happen in a major earthquake on the Hikurangi subduction zone and a damaging tsunami. I would like to introduce you to Dr. Caroline Holden, who is a seismologist and waveform modeler at GNS Science, and also Dr. William Power, who is a geophysicist at GNS Science. Those of you who tuned in last week would have also met my lovely colleague, Natasha Blunden. Natasha will talk as project leader of the Hikurangi Response Planning project, which is focused on putting all the science into practice here on the East Coast. Just before we get underway, we were aware last week that there were some issues with spam. Please remember this is a free event, so don't click on any links in the comments, and certainly don't provide any personal details like credit cards and so on. A little bit of info on how this will work. Caroline and William and Natasha will present first, then I'll facilitate asking the panel some questions. So if you have any questions, remember, no question is a silly question. Please write them in the chat box and we will be keeping an eye on these questions as they come in so we can ask them to Caro, William and Natasha. Anyway, over to you, Caro.
Thank you, Ben. Kia ora koutou, everyone. My name is Caroline Holden, and it's a pleasure to be presenting our teamwork to you tonight. So thank you for being here. Can you hear me fine, Ben and Natasha? Awesome. Okay, so I get started. Oops. Did I do that? Sorry. Hopefully I haven't. Okay, let's try again. Yes, excellent. Cool. So first I'd like to start with a bit of background. Earthquake scientists were tasked to develop or to prepare an earthquake scenario for the Hikurangi Response Plan. That scenario could not just be an imaginary earthquake scenario. It was constrained by three key conditions. The first one was that it had to happen on the Hikurangi subduction zone. So on that little cartoon here, that's quite a fancy 3D cartoon, the Hikurangi subduction zone is the contact zone between the subducting Pacific plate below New Zealand and the Australian plate coming into New Zealand. So that earthquake had to be rupturing the Hikurangi subduction zone. Second condition, it had to be very disruptive. So we expect on that scenario widespread ground shaking and widespread tsunami. And third condition, but very important one, it had to be a credible scenario. So in the next few slides, William and I will be showing first how we develop the recipe behind an earthquake scenario. And then we present the proposed earthquake scenario, but also we're going to be showing you some alternative scenarios that are equally important and should be considered as well. All right, so first we'll start with the recipe. So you've seen the fancy 3D cartoon before. This is my version of the Hikurangi subduction zone. It's meant to represent the Pacific plate subducting westward. So this is the Pacific plate subducting underneath the Australian plate. So this is my very personal 3D cartoon of the Hikurangi subduction zone. And the reason why I really wanted this one in particular is that it's showing the contact zone between the two plates. So the contact zone is our Hikurangi subduction. And this is where we have to be rupturing our earthquake scenario. Okay, so an earthquake is the result of a sudden movement of two sides of the fault plane. here are two faults, our plate, the Australian plate and the Pacific plates, right? So it's no surprise that part of the ingredients for this recipe will involve the earthquake parameters, right? What's happening on the fault itself when the earthquake ruptures. For earthquake scientists, these earthquake parameters are, we can control them easily. So we understand them and we can control them. We can actually play with them to satisfy the objective of the Hikurangi response plan. Now, there's a second type of ingredients that we cannot control as earthquake scientists, but we understand them really well, and they equally contribute to the impact of the scenario. And this is what I've called here our external parameters. So in the next few slides, we'll be looking at what are these earthquake parameters and what are those external parameters. Okay.
Okay, Ben.
So first, yes.
Sorry,
William.
Is it over to me? No, sorry.
No, I think wait. William's too keen. So I've lost my my screen now. Let me see. No. I think the PowerPoint has disappeared. While we're getting it up there, so I'll just sum up again. For our recipe, we need two types of ingredients. Ingredients that relate to the earthquake, surprise, surprise, and ingredients that are external to the earthquakes. These are really important as well. And so first I was presenting the earthquakes, the ingredients that are characterizing the earthquake. And one of them, once we're going to see my slide, one of them is the earthquake magnitude and size. So an earthquake is typically characterized by magnitude, right? That's the first thing you get from an earthquake. That magnitude is actually related to how much of the rupture, how much of the fault has broken, but also how much movement between the two sides of the fault has occurred as well. And so that's really important in our developing earthquake scenario. Now, if you had the slide, you would see three really exciting examples of what we had in New Zealand. So in New Zealand, we've had a decade of large earthquakes, but thanks to the GNS network, scientists have been able to look at these earthquakes in detail. And so we've been able to look at how much of the fault has ruptured, or what the size of the faults that ruptured in those New Zealand earthquakes, and also how much movement between the two faults has happened. So I keep going because soon we're going to have the slide. And so you'll see once you can see it, it's quite striking. So we have the Christchurch earthquake, which was a tragic, really sad earthquake that happened in Christchurch in 2011, a magnitude 6.3. That particular earthquake ruptured a relatively small fault, so 10 kilometer wide by 10 kilometer long. So 10 by 10 kilometer fault. Oh, there it is. Awesome. Yay. Okay, so this is what I'm talking about. When I'm talking about earthquake size and magnitude, this is the illustration of what I mean for the past earthquakes we've had in New Zealand. So the bottom one, that little blue square here represents this relatively small faults that ruptured in a Christchurch earthquake, 10 by 10 kilometer square area. Now, because of the proximity of the fault to the population, this earthquake became a tragic and very sad earthquake. If we look at the magnitude 7.1 Darfield earthquake now, that one that preceded the Christchurch earthquake, that one has ruptured about a fault that is about 40 kilometers long now by 20 kilometers deep. In terms of peak amplitude, for the Christchurch earthquake, we had about 3 meters of slip between the two sides of the fault. For Darfield, we had 6 to 10 meters slip between the two sides of the fault. And now we're looking at a more recent earthquake, the magnitude 7.8 Kaikoura earthquake. And this is the one that I've represented with the red and the yellow to red color gradients here. That earthquake ruptured a total fault area of 180 kilometers long by 30 kilometers wide. I have to say, all those little rectangles that you see on the screen, they are all up to scale. So it just gives you a sense of how we're going to estimate the size and the number. I didn't say the Kaikoura earthquake. We had a big slip of about or more than 20 meters. We cannot agree exactly on the value, but it was more than 20 meters slip that happened north of the earthquake around the Hikurangi fault, on the Hikurangi fault, north of the Kaikoura rupture. I'm just going to point it out now. It's going to be important later on in the talk. The particularity of the Kaikoura earthquake as well was that it ruptured unilaterally. So it started to the south. So it started near Hannon Springs, and it ruptured straight towards Wellington. So this is important for the next slide. Okay, so I've presented how earthquake size and magnitude is controlling ground shaking, right? The bigger the fault, the more slip and the stronger ground shaking you're going to get if you get close to that fault. Now, William is going to present how the size and the slip on the fault is affecting tsunami. Up to you, William.
Thank you. Hello, everybody. So I'm going to talk about how the earthquake properties control the size of the tsunami that gets generated. To try and explain that, I'm going to go a little bit through a cartoon version of the process by which an earthquake generates a tsunami. So we go to the next slide. So here we are at a subduction plate boundary, and we have one plate. In this case, this is our Pacific plate being subducted beneath the Australian plate. And in some circumstances, these plates can move past each other relatively smoothly. But in some situations, the two plates become stuck together. And as the plates get stuck together, they start to get bent. So you see this upper plate here getting bent as it's stuck to the lower plate that's being subducted. And this is storing up elastic energy in this plate. And at a certain point, it can hold back no longer. And at that point, we have an earthquake on the subduction interface, which is the boundary between these two plates. And this sudden springing back of the upper plate pushes up a bulge of water above it. And it's this bulge of water that is the start of the tsunami. So from that point on, the tsunami waves spread away. We have one wave heading out into the deep ocean and another wave heading towards the shore. Now, as you can imagine, the size of the bulge of water here is dependent on how much movement there is on this plate boundary. So the further the movement across this interface, the more water, the bigger the deformation of the seafloor, and the more water is displaced. So this amount of slip, this amount of movement is a key factor in our initiation of the tsunami. Now in these plots, we're just looking through a cross section, but if we imagine that this cross section extends into and out of the screen, we may find in a real earthquake that the amount of slip varies as you go along that direction. So that also, that variation in slip, as we say, along strike, along the axis of the fault plane, also has an influence on the amount of water displaced and the distribution of that hump of water that's initially generated. So that's why the slip distribution is really key to the tsunami generation, because it controls the deformation of the seabed, which in turn controls the amount of water displaced. So now I'll hand back to Caroline again.
Thanks, William. So we keep going on to the earthquake parameter side of the recipe for an earthquake scenario. So we looked at how large the fault can be and how much slip, how much movement within the fault controls the ground shaking and the tsunami generation. There's another parameter about the earthquake, which is the earthquake hypocenter. So the earthquake hypocenter defines where the rupture starts. So remember the Kaikoura earthquake, the rupture started very south of the rupture and ruptured all the way north towards Wellington. Well, for the Hikurangi subduction scenario, We can choose to have an earthquake that starts, south and ruptures all the way to East Cape. Or have an earthquake that starts near East Cape and ruptures all the way south towards the Wairarapa. Now you're going to think, well, who cares about a hypocenter? We've got this mighty fault, right, with lots of slip, more than 20 meters slip. Surely, how close you are to the fault really matters more than how, the direction for which the rupture is happening. Well, just to illustrate the point that earthquake hypocenter is really important, I've taken again the Kaikoura earthquake, and I'm going to show you the effect of what we call rupture directivity. So here you see 4 recordings of the intensity of the ground shaking at 4 locations in New Zealand. So 4 locations along the Kaikoura earthquake faults. These are thanks to the National Seismic Network, GNS. This represents 3 minutes of shaking. So it's quite a decent size, decent time of shaking. And what I want to illustrate here is that the earthquake started near Hanna Springs, right? So in Hanna Springs, we have strong shaking at the beginning of the earthquake, and then we have moderate shaking that lasts for 2 minutes, about 2 minutes. Then the earthquakes propagate towards Kaikoura. Kaikoura, we get strong shaking because we have a big fault that ruptured near Kaikoura, and moderate shaking that keeps going for another minute. Now the last city that was critically impacted was Wellington. Wellington was about 300 kilometers away from the epicenter. Wellington was 80 kilometers from the fault plane. However, you can see that on the slide, the shaking was actually really strong. And this is due to what we call rupture directivity. So this is the earthquake starting south and packing all the energy, propagating it towards cities that are in light of that rupture. So if we're looking at the rupture coming towards us, we're going to get amplification of the ground shaking. But there's also some good side of directivity, because if you're behind the rupture and the rupture ruptures away from you, like what happened in Christchurch for the Kaikoura earthquake, you're going to get a lot more moderate ground shaking. So just to illustrate that the earthquake hypocenter is critical in our recipe for an earthquake scenario. Okay, so to summarize, we looked at the earthquake parameters, earthquake size, so fault rupture size, and also how much slip has happened between the 2 faults. It's really critical for strong ground shaking, but also for tsunami generation and earthquake hypocenter as well. Now we look at the parameters that are out of our control. That's called the external parameters. And but these are equally important in terms of the impact of that earthquake scenario. So for ground shaking, the parameters that actually really contribute to amplifying or decreasing the ground shaking felt at a particular site. So here is our little house here that's going to feel the effect of the Hikurangi subduction rupture in there. What's really important is the path that the seismic waves take when they go all the way from the Hikurangi fault all the way to your building, your house, or your bridge. So that path is actually really important because it can amplify the ground shaking or it can attenuate it as well. So this is controlled by the geology, and it's actually it's happening at different scales. We have the regional geology, which is at 100 kilometer scales, that can amplify or attenuate your seismic the shaking caused by the earthquake. So for example, in the Taupo volcanic zone, we have a crust that is really hot and tends to attenuate the ground shaking a lot. A magnitude 5 near Taupo will not feel the same as a magnitude 5 in Christchurch, for example. But we also have the local geology, or the shallow site effects that are close, that are local to your buildings or your house. And that shallow geology, it could be the very thin sediment deposits, but also could be local 3D structures like the Wellington Basin. So this kind of local geology parameters will also influence how strong the shaking will be at your site. Now, this is what the parameters control for ground shaking, but we also have some external parameters that will control how the tsunami is responding to the earthquake. And so this is when William takes over and explains this better than I do.
Okay. Right, so for tsunami, we have a similar situation. So we've already talked about how the slip and the seabed deformation initiates the tsunami, but the size of a tsunami as it reaches the coast is influenced by the propagation of the waves, so the spreading out of the tsunami waves as they move away from the source. And this in turn is controlled by the shape of the seabed. So essentially what happens is that the tsunami waves travel at different speeds depending on the depth of the water. So they're traveling faster in deeper water and slower in shallow water. And this effect can change the direction that the waves propagate. So it's very similar to refraction of light in optics, where if you have light that goes through a prism, it travels more slowly through the glass and it sort of gets bent to a different direction. And the same kind of things happening for tsunami waves, but that bending of the waves is controlled by the shape of the seafloor. When the tsunami wave reaches the coast, the height that it can reach onshore is affected by the shape of the topography, the shape of the land. So we often see the larger tsunami run-up heights in situations where the tsunami gets, for instance, funneled into a V-shaped valley. So if you imagine a tsunami coming onshore and it comes to a valley that's getting narrower and narrower, the water gets squeezed into a smaller and smaller place, and the water level tends to rise highest in those kind of situations. So back to Caroline.
Thanks, William. Okay, so now we're looking at the product of this recipe. We looked at the proposed scenario. So on this figure, we've presented the rupture area that will occur between the subducting Pacific plate and the Australian plate. So this is the colored area represents the zone that will rupture in that earthquake. So it's quite a large rupture area of about 500 kilometers long by 150 kilometers wide. What you can see as well is there are different colors, and these colors represent how much slip, so how much movement is happening along the fault. Oh, sorry, I'm trying to swap. I forgot to point out that this, the rupture area of 500 by 150 kilometer region is actually part of our objective to stay credible. So it is consistent with past paleoseismological studies of the Hikurangi past earthquakes. So in that sense, it fits with the credible side of our objective. That area, I have to say again, I forgot to point it out, sorry, it's equivalent to magnitude 8.9. In terms of how much slip is happening, or how much slip we're going to put on that particular fault, like William pointed out before, we want widespread tsunami, so we want a lot of slip happening near the ocean floor. So we have a region here that has concentrated slip near the trench, so near the surface. But also you will notice a patch of red slip here. Recent geodetic studies are actually telling us that the two plates, so the Pacific plates and the Australian plates, are actually stuck in the southern part of the Hikurangi zone. So they're really strongly coupled and they're stuck and they're accumulating strain. And so we believe that when that strain is released one day, it's going to be released in an area that will have a lot of concentrated motion between the two sides of the fault. And so again, to keep our scenario credible, we have allocated a lot of slip to be occurring in the southern part of the Hikurangi zone. Now the last parameter, which is a hypocenter, remember how it's important. Unfortunately, there was no evidence to actually tell us where we should be rupturing on the fault. And so we just put it in the middle, and we have what we call a bilateral rupture that ruptures equally to the north and to the south. All right, so what are the consequences of that particular scenario? We look at the consequences in terms of its impact of the impact of ground shaking and the strength of the ground shaking and the strength of the tsunami that's been generated. The figure here illustrates how strong the ground shaking from that, the resulting strong ground shaking from that particular scenario. So it's expressed on an MMI Mercalli, modified Mercalli intensity scale. It's a convenient scale because it's actually representing the effect of ground shaking on the human and the built environment. So if we're looking at MM6 or 7, we have very strong shaking. So everything that is yellow represents very strong shaking. Everything that's past yellow is severe shaking. So on this map, you can see that there will be very strong shaking felt all across the North Island and the top half of the South Island. There will also be severe ground shaking, widespread severe ground shaking all along the east coast of the North Island. And this is due because of the proximity of this region to the fault plane and therefore to the slip, and where most of the action is happening. What this map is not showing is how long the shaking will be. So you have to imagine that to rupture this 500-kilometer long fault, it will take minutes, so 2 to 5 minutes. And so the shaking, the resulting ground shaking will also be extremely long. So we not only have strong shaking, but also very long shaking. Now, in terms of the impact, looking at the tsunami impact from that scenario, it's illustrated here in a scale that's looking at the maximum water height at the coast.
Height offshore in that plot, Kelly.
Offshore, okay, not at the coast. Thank you, William. And as expected, you can see high amplitude of the waves in the southern part where we had a lot of slip, concentrated slip happening in that region, but also widespread high tsunami waves along the coast of the east coast of the North Island. An interesting point on that picture is of the tsunami impact of that particular scenario is that we have very little impact for the region in the Bay of Plenty region and to the west of Bay of Plenty. So this is one proposed scenario, but there's no reason not to consider other scenarios, because actually we can keep the magnitude the same, we can keep the fault area the same, but we can play with other parameters that would also be credible. So for example, here we have our original scenario, the part that ruptured from our scenario, but we can also shift this to the north. We can also change the slip distribution, so how much movement is happening on that fault. And we can also move the hypocenter. We can decide to look at the effect of the hypocenter rupturing from the south to the north and from the north to the south. And so William is going to show the effects of those alternative scenarios.
Okay, thank you very much. So what we picked out, excuse me, I've jumped one. I need to go up. Oops. Do I have the control now, Ben? Yeah. So we picked out for the main study one particular earthquake scenario, but we can't predict in advance the details of what kind of earthquake will happen. So it's important to understand that there are many different possible scenarios and that their consequences could be quite different. So here we've taken an earthquake that's essentially the same in terms of slip distribution to our original scenario, except that we've shifted it about a few hundred kilometers further to the north, so that instead of going from Cook Strait to Poverty Bay, we're starting from North Wairarapa and extending north of East Cape. So in every other respect, this is the same scenario, but by moving the earthquake further north, and we can't tell, we have no strong reason for saying where future earthquakes are specifically going to be on the Hikurangi plate interface. If we have something like this that extends north of East Cape, we get a very different distribution of the tsunami. So in this case, there's not much tsunami down in Wellington, but we have much more tsunami impact through the Bay of Plenty, Coromandel, Great Barrier Island, Northern Auckland, and so on. So quite different parts of the coast can be affected by shifting this earthquake, this rupture, further to a different location. Now, even if we stay in the same location, but use a different distribution of slip, so a different distribution of movement on the interface, that also gives us different consequences. And yes, once again, we don't know how this distribution of slip will look like in the next similar real event. So this is just one, so our study is based on one single possibility. If we use a different distribution of slip, and there's no strong reasons for preferring any one possible distribution, we get different consequences. So going across the top here, we have the consequences in terms of seabed deformation and offshore wave heights from our standard model. And here it is for just one of many different alternatives that are the same magnitude and roughly speaking in the same location. But here you see we get a different distribution of movement on the seafloor, and this produces different tsunami waves. So if we have an earthquake that looks more like this scenario, we're getting bigger tsunami waves along the Wairarapa coast, but in this case, smaller waves around Wellington and slightly smaller in Hawke's Bay, for example. So this is just trying to emphasize that we've focused on one scenario to look at the details that can occur, but there are many different possible scenarios, even for the same magnitude and general location. Now, Caroline talked about the sensitivity of the earthquake shaking to the hypercenter location. And you remember our standard model has the hypercenter, roughly speaking, in the middle of the rupture. But we can look at alternatives where, for instance, the hypercenter is at the north end of the rupture and it propagates and the rupture spreads down towards the south, or the reverse where the hypercenter is at the southern end and the rupture propagates up towards the north. Broadly speaking, in the case where we have the hypercenter to the north and the rupture coming south, we get greater shaking at the southern end of the Hikurangi interface or beyond the southern end. And when we rupture from south to north, we get stronger shaking to the north end of the rupture. So this is again illustrating the sensitivity to a particular parameter that we can't know in advance. So there's much more to the consequences of an earthquake than just its magnitude, is really the take-home point here. Now, one of the other questions we'd like to discuss around this scenario is the question of the likelihood. So how probable, how likely is a earthquake that is in broad terms similar to the one that we have used for the Hikurangi Response Plan? And I think the best way to discuss this is by looking at the work of Kate Clark and her colleagues. Some of you may have seen Kate's presentation last week, but she and her colleagues have looked at paleo tsunami and paleo deformation at the coast, so paleo earthquake signatures, and use that to construct the sequence of past large earthquakes on the Hikurangi subduction zone. So these figures here show reconstructions of different past earthquakes over the last, well, roughly 7,500 years. And we can see that if we look for the ones that are more or less whole margin earthquakes or covering a similar large extent to the Hikurangi Response Plan scenario, we see that this particular scenario is quite similar and is there's moderately good confidence that this is a true event. And there are these two other scenarios that also look like they are similarly large Hikurangi earthquakes, but these two we have slightly less confidence in them. So it could be that that there's enough uncertainty in the measurements that we're slightly unsure about these two, but we're fairly confident about this one. So over this last 7,500 years, we have between 1 and 3 scenarios that are, broadly speaking, similar to our Hikurangi response plan scenario. So we may say it's somewhere between a 1 in 2,500 year event and a 1 in 7,500 year event, just broadly speaking. And of course, as we've already tried to emphasize, each of these events will have its own unique property. So none of them will be, exactly the same as the Hikurangi response plan scenario, but they're broadly similar in terms of their overall dimensions. So that's the conclusion of the scientific part of this presentation from Caroline and myself. We'd just briefly like to acknowledge some of our colleagues. So Yoshi Kaneko played a big role in the earthquake modeling, and my colleagues Christoph Muller and Xiaoming Wang played a big role in the tsunami modeling. Oops. I just briefly mention, so although not much, this will be more discussed in the next talk. Julia Becker and Shenglin Lin were influential, played a big role in the impact assessment. And with that, I'll hand you over to Natasha. I think you're muted, Natasha.
I was, thanks, William. Hi, everyone. My name's Natasha Blunden, and as Ben said at the start of the talk, I'm the project leader for Hikurangi Response Planning, and I work out of East Coast Life at the Boundary. So I've got the exciting job of taking all this fantastic science that William and Caroline produce and analysing it a bit further to see, how might this play out, what might the impacts be, and how can we plan for this and make our communities more resilient before it happens. So we've talked a little bit around what a scenario is, and I just want to briefly go over why we use scenarios. So for the last 2 years with the Hikurangi Response Planning project, we've used a magnitude 8.9 scenario, which is what William's just described. And that's been used to inform how we plan. So scenarios are kind of a description almost of possible things that could happen in the future. And they're useful for planning, especially for planning for things that we haven't experienced before. They don't predict the future, and that's a really important point to take away, but they are really useful for us to look at these things that haven't happened before. So the HRP scenario was developed to help see what the impacts might be of a credible magnitude 8.9 Hikurangi subduction zone earthquake and tsunami. So several were developed, as we've seen. There's been a couple alternative scenarios, but we've picked one as a basis for talking to our stakeholders, and I'll show you a few examples of some things we've found through using that scenario tonight. Before I move on, I just want to reiterate that a future event, it could be one of thousands of scenarios. Like William and Caroline said, there's really no way of knowing what the next large Hikurangi event will look like. But again, these scenarios, we use them as tools and they're really useful for that. So as I said, after we began the project, GNS Science produced the scenario report, and we had to undertake a few actions to then translate that into something that we could give to emergency managers and organisations to help them plan for this risk. And all of this information is being compiled into a response planning toolbox, which is being released later in July this year. Cool. So how did we do that? How did we drill down into the scenario to see how that's going to impact our communities? What we did, we held 5 workshops across 5 civil defence groups, and a range of stakeholders participated in those workshops. I've put a few logos up on the screen, but this really doesn't cover how many people attended. We had about 400 experts over the course of 2 months help us to look at the science and discuss, what would be our priorities in this event? How would this impact our communities, especially along the coast? and what would be our key actions that we'd need to undertake following a large event like this. So it was quite useful during those workshops to use some of the work. There's been a lot of work done already, I guess, in terms of vulnerability of our coastal areas. There's lots of maps out there that we were able to overlay over the inundation, so where the tsunami might reach or where the shaking might go. And by looking and comparing different maps, we were able to identify key infrastructure that might be at risk. And identifying vulnerable infrastructure like this is really important, not just for response planning, but also for looking at how we can increase the resilience of our cities before an event happens as well. So all in all, we collected a lot of information from these workshops, which is fantastic. But what it really drilled down to at the end of the day is that a large event like this would be a catastrophic disaster for New Zealand. This is going to be something that we'd never experienced before. So that's why it's all really important that we take steps to prepare. And it's really straightforward to prepare. We can all do it. I've done it myself. It's as simple as checking to see whether you live or work or tend to visit tsunami evacuation zones, practicing your tsunami evacuation route. So how are you going to get to high ground or inland? Making a household plan with your family and your friends that you might live with, and also making a go bag that you've got at work or in the car or at home. But one thing that I really want to make clear, and that we've seen very recently, is that our team of 5 million, we are resilient. So I have said that this would be a catastrophic disaster for New Zealand, but you only have to look at recent events to see how well we all pulled together in the face of adversity. And this really gives me a lot of encouragement for how we would handle a large Hikurangi event. So do keep this in your back pocket, that, you know, we've got through a really significant event and we're still going through it. And we can use the skills that we've learned from this in any future hazard event as well. So in terms of the impacts, I'm just going to touch quite briefly on the impacts. Next week, our talk is going to be going a little bit more into what the impacts are. But generally, the impacts of a large event like this on our communities would be vast. We would have displaced people. So after people feel a long or strong earthquake, we'd hope that they would evacuate inland or to higher ground. And this might mean that some people become separated temporarily from their families. As with a large event, of course, there would be people who would be injured, unfortunately, and there is the potential for fatalities. And there would be large demands on our frontline staff. So this would be a huge event for our emergency services to deal with. Because this event would impact a lot of us, it might mean that we don't continue to live for a while. It might mean that we're out of work for a while. There would be increased need for some support to help us to get through the disaster. And of course, because it's such a big event, our economy would take a bit of a hit, and there would be some long-term psychological impacts there. In terms of our way of life, I've just got an example diagram on the side there. That's from the magnitude 8.9 scenario. So as we've said, it's really hard to predict how these things are going to happen. So this is just an example. But, you know, really think about what you'd do without no power, no water, no telecommunications, so no cell phone coverage, or, you know, no ability to go on Facebook. And if you haven't thought about it, excuse me, think about having a torch. Think about some water, storing some water at home, how you would have a wastewater system, so a temporary toilet, and also how you'd keep in contact and get updates through radio. So, excuse me, I got a frog in my throat. That's everything from me, but we'll go to questions now, I think, for Ben. And I'm going to go grab some quickly.
Awesome. So I guess, first of all, a big ka pai, and thank you to our three speakers. They've provided a very thorough overview of the science behind the scenario. It's certainly a fascinating area of science, and as you've shown, and also Natasha has sort of illustrated, it's incredibly useful for planning. I'm now going to ask the three of you some questions, and if other viewers have questions, keep them coming in on the chat box. There's quite a few questions coming in, but seeing as I'm the guy with the mic, I'm going to indulge myself in the first question, because I'm really curious to know how William and Caro down in Wellington and Natasha here in Napier have prepared themselves for an event the scale that we're talking about here with the credible scenario. Do you want to fire away, William?
Sure, Ben. So for myself, where I live in the hills in northern Wellington, I'm quite well above the tsunami evacuation zone. And similarly, where I work in the Hutt Valley, although it's relatively low down, is a long way from the coast, so is also outside of the tsunami evacuation zone. However, what could be quite difficult for me if there is a big earthquake like this while I'm at work is returning to my home, which is difficult to do without going close to the shore. So because of that, we have made arrangements with other parents to look after our children in this situation until such time as either myself or my wife can get home. And in that way, we can, in the first instance, focus on our own safety during the earthquake itself and not have to be, well, we will know our children are being looked after while we try and make our way home. So that's very important to us. And I think that's probably one of the key things from me.
Cool. How about you, Natasha?
Yeah, so I live in a tsunami evacuation zone. And when I first moved, I was a little bit concerned, but once I looked into the risk and understood how I could actually prepare, I felt a whole lot better about it. So my husband and I, we tend to go on evening walks. So we'll practice our tsunami evacuation route quite regularly, actually. And we also practice a couple different routes because it's important to note that you might not be able to use the right evacuation route on the day. So we make sure we do a couple of evacuation routes. I've got a couple go bags. I've got one in my car, at home, and at work, because I work in a tsunami evacuation zone too. So yeah, at work, we regularly do drills on Tsunami Hikoi Week, and I'd really encourage anybody else to do that too. That's really useful.
How about you, Caroline?
Yeah, just like William, it was about having a plan for the family first. So after the 2013 Cook Strait earthquakes in Wellington, there was a wake-up call that we didn't have a plan about who was going to pick up the kids. And so once that's sorted, it's yeah, I feel a lot better about it. And the second part is we have a rainwater tank at home now. So it's about 200 liters of water that we can count on if we use water for following an earthquake. So that's also quite makes me feel better as well.
I think some councils are kind of, especially Hawke's Bay Council, is helping out with water tanks and that sort of thing as well. So there's a few initiatives happening. So that's a really good point. I'll move on to some of the audience questions now. There's some bangers. So the first one, what's with the earthquake activity off the coast of Levin at the moment? This big kind of crazy cluster that's happening.
I guess I'm going to answer that one. Yeah, so that earthquake was felt quite widely. It was a nice gentle shake for a long time, for a long gentle shake in Wellington. Because of the magnitude 5.8, it had quite a decent aftershock sequence, and location of these earthquakes are close to the shore. Quite shallow as well, and so the aftershocks are being felt as well. So from discussing with my colleagues, there's nothing unusual about the intensity of the aftershock sequence, but it's just they are being felt quite strongly because of the proximity to populations.
So it's not unheard of.
No.
Do you have anything to add, William, or you leave that to Cara?
I think in terms of the geophysics, I think Cara has covered it well. I think it's worth mentioning that there are offshore faults along that coast that are potentially large enough to could potentially have an earthquake large enough to cause a tsunami. So it's important to keep in mind that people should observe, if they live near the coast, the long or strong get gone message.
Excellent. Okay, so the next question, is there a rule of thumb for magnitude of earthquake and height of uplift, e.g. for a magnitude 8 or a magnitude versus a magnitude 9 earthquake?
William?
Well, there are general scaling laws, so that if we know the magnitude of an earthquake, we have a rough idea of how big the rupture is likely to be and how much slip there's likely to be. But the amount of seabed deformation is also dependent on things like how deep the earthquake is as well. So there isn't, so there's a partial, to some extent we have a feeling of some of the earthquake properties, but it's not quite so simple to translate that directly into the amount on the sea of uplift on the seabed.
So you can't necessarily say whether a magnitude 9 will have, you know, or a magnitude 8 and a magnitude 9 could still have a very destructive tsunami triggered.
I mean, there are broad rules of thumb about how the size of tsunamis scale with magnitude, but there's a lot of variation as well. So, I mean, very roughly for each unit of magnitude, the size of tsunami tends to increase by about a factor of 10. So between a magnitude 8 and a magnitude 9, you very roughly speaking get 10 times as large as the tsunami. But this is very, very approximate rule of thumb. So yeah, we can have some sense, but the details really do matter a lot.
Yeah, that makes a lot of sense. Next question, do you think tsunami evacuation zones are high enough for a magnitude 8.9 earthquake? That's a really interesting question. It's pretty gnarly.
I can probably talk a bit to that one. So typically with tsunami evacuation zones, when they're designed, they take into account several different scenarios. And our magnitude 8.9 credible scenario is definitely one of those which people do take into account. So that's why we say every step counts when you're evacuating from a long or strong earthquake, because you never know if it's going to be a small event or a large event. So yeah, every step counts, and the zones are based on multiple different parameters and scenarios sometimes. So definitely the 8.9 is factored in there.
So if you got out of the particular zone and, like, you know, you just want to get as far away from the coast as you can, or yeah.
For sure, yeah, definitely. And you've always got to remember when you're evacuating that there's going to be people behind you as well. So you need to leave room for them as well. So if you're particularly evacuating up a hill, keep going as far as you can. It won't hurt to go the extra distance, and that will make room for people coming in behind you.
Cool. I'm not sure if you guys have thought much about this, but how much damage would a magnitude 8.9 event do to the average house?
I think that one probably
Caroline?
on a lot of factors involved in that one, including, you know, the geology that the house sits on, which would affect the way that it responds, and the materials it's made out of, and you know how old the house was. So I think that's a really hard one to comment on, but if people go to the EQC website, they can learn all about how to fix, fasten and forget, which will really help with the contents inside your house. And I think there's also tips there as well with foundations strengthening and whatnot. William and Caroline might want to add to that, I don't know.
Yeah, no, that's an excellent answer, Natasha. Yeah. Just, you know, from the recent Hikurangi earthquake houses that were very close by, the small one-story wooden flexible houses did pretty well. So yeah, it depends on the strength and the length of the shaking as well.
Yeah, I'm from near Christchurch, and it was always sort of that interesting story about how Wellington houses, because they had that earthquake back in 1855, they sort of built their houses in wood, versus people in Christchurch thought that, you know, the earthquake wouldn't happen there, so it was all bricks and mortar, and it was less flexible. That's the thing. So Interesting thing to reflect on, I guess, if you're building a house, especially on particular geology.
Yeah, another point was that in Wellington in 1942, we had a lot of strong earthquakes, and so a lot of chimneys fell down during those earthquakes. So it was interesting to see that in Canterbury after the Darfield earthquake, there was a lot of bandage on top of lots of chimneys that had toppled from that earthquake. Whereas in Wellington, we've already had it in the 1940s.
People don't have sort of big brick chimneys in Wellington and those sort of places, do they, so much? Is a Hikurangi or an alpine fault rupture more likely? Another gnarly question. They're good tonight.
But the alpine fault is certainly has more detailed studies because of its land footprint. And so we have very detailed studies of the past earthquakes on the alpine fault in terms of the frequency of those earthquakes and the extent of them. And so they do see that it seems to be occurring fairly regularly every 300 years, and the last one was 300 years ago. So there is a high likelihood of an alpine fault earthquakes in our lifetime. Whereas the Hikurangi one, the uncertainty is a lot wider, and also the size of the earthquakes are a lot bigger as well, and so increase the uncertainty on the likelihood as well.
Oh, good answer. Do large quakes lead to greater volcanic activity?
Sometimes. We need a volcano expert. There is evidence for triggered volcanic activity following an earthquake, large earthquake. There is triggered hydrological activity following large earthquakes, even in New Zealand after the Hikurangi earthquake, thousands of kilometers away. We've seen springs bubble following the Hikurangi earthquake. So there is definitely some non-earthquake activity that is triggered after a large earthquake. In terms of volcano, my volcano colleagues would be better suited to answer this one.
Yeah, I guess there's some understanding that it's all a linked system, isn't it? So the subduction is causing the volcanoes and that sort of thing, and it's a constant kind of process. So yeah, but there's no kind of predictability to some extent, is there?
That's right.
Yeah. I have another few questions. It's great. When you say the fault area of 500 kilometers by 150 kilometers squared, does that mean that some of the width is very shallow and some is very deep? Does depth impact strength?
William, do you want to answer this one?
Well, yes. There is variation in the strength and the rigidity of the crust around the fault. It varies both sort of up and between shallow and deep, but it also varies along the length of the Hikurangi subduction zone. I'm not really an expert, but broadly speaking, we feel that the rigidity, the stiffness is less as you get to the shallow parts, and stronger as you go deeper.
So what does that mean, William? What does that?
It can be quite a complicated story if we have earthquakes that are only on the very shallow part of the Hikurangi plate interface. So in 1947, up near Gisborne, there were 2 earthquakes that were up on this very shallow part of the plate interface, up in the East Cape region. And because they were in this area where the plates are not very stiff or have low rigidity, we had a situation where there was quite a lot of movement of the seafloor. So we got 2 tsunamis, a tsunami in each of the 2 earthquakes in 1947, but the earthquakes weren't very strongly felt. So these shallow earthquakes, sometimes people don't necessarily feel particularly strong shaking, but you can still get a strong tsunami. And this is one reason why we always say long or strong. And it's important to remember the or, because in this case, you had earthquakes that were quite long. So they were going on for maybe 3 minutes or so, but the actual shaking was relatively gentle. So we need to be aware of that, particularly, well, we know that can occur up around Gisborne, but that's one of the implications of the fact that that stiffness varies depending on how shallow or how deep you are.
It's good to see someone followed and remember those numbers.
I feel there might be a seismologist in the audience.
Right.
That's a little bit clued up on this stuff because these are pretty good questions. I have one final question, and it's how will this scenario impact Palmy North?
Fantastic question. That's fabulous. I think I saw it, was it Sandra that asked that? Great question, Sandra. So in terms of Palmerston North, obviously this credible scenario is just one of many different scenarios. So, I mean, we have looked at the impacts in that area, but the next event could mean that it's completely differently impacted. But in terms of the credible scenario, the impacts that we have for Manawatu Wanganui is that it's likely you wouldn't really have wastewater or potable water for about, longer, for at least 7 days. And also you might have a bit of telecommunications loss and power loss there. But it is, compared to the East Coast, relatively less impacted. So yeah, Palmerston North's an interesting location because you're right, smack bang in the centre. Don't know if William and Caroline want to answer anything else onto that?
Yeah, no, in terms of the shaking, definitely not severe like the East Coast would be feeling it. But it would be long shaking, when you felt Kaikoura was so far away and it was still 3 minutes of shaking for Wellington. So the long shaking anyway, hence the disruption. But again, you're away from any tsunami inundation zone as well. So
Sandra might have a little bit of this clarified next week if she tunes in, because I think this is kind of edging into what we're going to be talking about with William and Caroline and Julia next week.
Yes,
would you agree? Yeah, I think stay tuned. So that brings us to the end of all the questions this evening. Firstly, massive big thank you to Caroline, William and Natasha. It's been really insightful. And very, very brilliant to hear how the scenario was developed and what the kind of aspects that were brought in to kind of consider it and make sure it was credible and realistic. Yeah, as Natasha said, there's a third virtual talk next week. It's at the same time, 7 p.m, but it's not on Thursday, it's on Tuesday. And yeah, this talk will cover how the event we've covered tonight will impact different parts of the East Coast in different ways. And that's related to aspects such as location, geology, and so on. The more the merrier. So please encourage your friends and family to tune in, especially if they couldn't make it the previous 2 Thursdays. In addition, if you want to learn more, visit the East Coast Lab YouTube page. There's heaps of really great resources there. Particularly into the science and with Laura and Kate and William and Caroline, who we've heard from so far in this series. And there's various other just cool graphics, videos, and some information on preparedness. There's also, if you want to find out more, there's some sites that you can visit. The getready.gov site, the East Coast Lab site. And various other response resources. You can also follow us on New Zealand East Coast Lab on Instagram and Twitter. And you've all found us on Facebook because you're tuning into this. So yeah, thanks for coming along. Stay safe out there and Hamarie.
Thanks, Ben. Thanks, Natasha.